Welcome back. Previously, we used regular expressions to generate complex finite automata or finite state machines to recognize a pattern in an input string. Here, we are going to extend our syntax to be able to specify not just a single letter for a pattern, but a range of letters for a pattern. This is extremely useful when looking to identify something like a number, where any character between 0 and 9 will continue to match the pattern. Originally, our atom code just looked for a single letter. Let's go ahead and write a new function to look for a range. Our range will start with either a letter or a digit, followed by a dash, and then another letter or digit. We will also check to make sure that the range concludes with a square bracket. If all of these conditions are met, we will create a new state, add this range as an output, and then return the newly created state. We've used a number of control characters in our regular expression, such as the plus sign to indicate that we expect to see one or more of a letter. But how do we actually find the control character itself in our pattern? To do this, we will add an escape sequence. The escape sequence will start with a single backward slash. The character which appears after will be interpreted literally, such as a left parenthesis or a left square bracket. We will create a new state, add a single output of this character to the state, and return that as the result. Now that we've added methods to look for a range of characters or an escape sequence for a control character, we can go back and modify our original atom function. In this case, if we notice a beginning left bracket, we will check to see if we are parsing a range. Similarly, if we notice a single backward slash, we will actually parse our escape sequence. By modifying this function, we're able to look for more than just a single letter, but actually a range of letters or a control character in our regular expression. Let's go ahead and run a few tests with our newly modified regular expression. Now, instead of looking for an A followed by one or more B's, we can look for a sequence of A or B's. Similarly, we can modify this to the entire range of letters and looking for one or more of any letter between A and Z in a sequence. We also add the ability to look for an escape sequence. In this case, we'll be able to look for a single left bracket, which is typically used for our range operator. However, now we will use a backward slash, and we have to use two, one to escape the slash in the string, and one to actually represent the backward slash that will be in our regular expression, followed by the left bracket. You can now see in our test case, we successfully identify a single left bracket as an identifier and not just a control character in our regular expression. As mentioned in the previous video, we are writing a recursive descent parser to read our regular expression. However, up until this point, there's been no recursion as none of the parse functions actually call each other. We will now add parenthesis control characters to our regular expression. This will allow us to group sub-expressions and now look for various patterns within the larger pattern. As an example, we can now find an A or B and one or more of either an A or a B, grouping them with a parenthesis. To achieve this, we will modify our atom function to look for a single left parenthesis. If we find a parenthesis, we'll assume that we are parsing a new sub-expression, and therefore call our original parse expression. We will also have to modify a few of our other methods to handle this new parenthesis control character. With our newly created recursive descent parser, we can now go back and using the parenthesis, look for an entire sequence of either the letter A or Z. With these few simple additions to our regular expression, we are now able to return to our original goal of identifying numbers and identifiers in a string. An identifier always begins with a single character followed by one or more letters or numbers. We're now able to use our regular expression parser to automatically generate a complex finite state machine that can identify this pattern. However, what if we also want to identify numbers? In this case, we will create a new finite state. We will add an empty transition to the start of each of the machines defined by the regular expression. Calling scan from this new start will allow us to look for both identifiers and numbers in a string at the same time. We have successfully used regular expressions to automatically build complex finite state machines capable of matching patterns in strings. In our next video, we will combine these techniques to form a lexer, which is a critical component of a compiler or any program which is looking to parse a language.